This is lesson 11 in Electronics 2. We are going to start today by kind of cleaning up some stuff, some things that I left out from before, some kind of information on performance parameters of op amps I didn't talk about, performance parameters of audio amplifiers, and then we're going to move into DC to DC converters, which is some really fun stuff. So let's start with gain bandwidth products. So this is an op amp parameter that I didn't mention. I may have talked about it before, but we're going to talk about it more explicitly now. So one of the things you noticed in lab is that op amps have this thing where the output can't respond infinitely fast. So when the input changes, the output in response will change according to the gain, but it doesn't necessarily change instantaneously. And what that means for frequency response is that your op amp has sort of an upper limit for frequency. I mean, you can think about it, right? If the slope of your op amp, you sort of measured the sort of maximum slope the op amp was capable of producing in its output, and think about it. If you are trying to make a sine wave, right? A slow sine wave is going to be something, a slow sine wave is going to be something like this, But at a high enough frequency, right? At a high enough frequency, okay. At a high enough frequency, that slope, if you zoom in, right? At a high enough frequency, that slope is going to be too steep to where, that's going to be steeper than that maximum slope that you found, the slew rate that you found earlier. And that's ultimately the source of the frequency limitation. So op amps do have a frequency output limitation, but it's not just a frequency limitation, because let's say you took this exact same frequency. Let's say you took the same frequency and you decreased its amplitude. Well, if you decrease this thing's amplitude enough, if you decrease its amplitude enough, that's not the same frequency, but oh no. So if you decrease its amplitude enough, that same frequency signal would have a lower slope, right? So that same frequency would have a lower slope just by lowering its amplitude. And that brings us to this notion that for op amps, there's a limit, which is kind of set by the slew rate of the gain times the bandwidth. So the product of gain and bandwidth is limited in op amps, meaning that, right, you can have, if you have a very high frequency, in order to stay underneath that sort of slope limit set by the slew rate, you have to decrease the amplitude a lot. If you have a very low frequency, you can have a very large gain amplitude and still be within your slope limit set by your slew rate. So you can view this if you look at sort of performance parameters. So this was pulled out of, this graphic was pulled out of, I think, an LM358 data sheet. And so this basically shows frequency versus open loop voltage gain. And with most op amps, there's sort of a plateau. There's sort of this peak open loop gain, and that's what we measured in lab as sort of the DC open loop gain. But as frequency increases, this starts to roll off. So as frequency increases, this starts to drop. And eventually you'll reach a point of unity gain. And when you reach that at a certain frequency, when you reach unity gain, that's where your gain is 1, right? I say gain is 1, but it says gain is 0. Why? It's a log scale, right? So 10 to the 0 is 1, right? So gain of 1 is 0 dB. And it's at that frequency that you can determine what the gain bandwidth product of your amplifier is. So you can just read it. If you're looking at this data sheet, reading this is, we have 2 lines here, which is probably sort of the range of values for this. And so it looks like it's, about maybe 900 kilohertz based on looking at this. We might be able to see it a little bit better here, right? So we might be able to see it a little bit here. So we have at 1 kilohertz, we're about dead center between that range there. And what's the gain here? The gain is 60 dB. Well, what's 60 dB? That's 10 to the power of 3. That's 1,000. So gain of 1,000 times 10, yeah, about 1 megahertz is about, looks like from looking at this data sheet, 1 megahertz is about the gain bandwidth product of this amplifier. Okay, So let's do an example. Let's do a practical. Oof, gave away the answer there. Let's do a practical example. So you're using an audio quality op amp with a gain bandwidth product of 500 kilohertz. Assuming your amplifier must function up to frequencies of 20 kilohertz, what is the maximum gain non-inverting amplifier you can create without reduced gain at high frequencies? Okay, so to just do this very simply, we have the gain bandwidth product equals the gain times the bandwidth, also known as the frequency, right? The bandwidth is a term that has a lot of different meanings, but for our purposes, it means sort of the upper frequency of operation of our signal, right? So in this case, if we have 500,000 equals X, which is our gain. Let's change that to G. Gain times our bandwidth is 20 kilohertz. And now that I think about it, I did it on the slide. So yeah. So, so the maximum closed loop gain is the gain bandwidth product divided by the frequency. 500,000 divided by 20,000, that's 25. It's important to keep in mind. So a lot of times students forget this. They forget that they'll build a high gain amplifier and they'll forget that there's a limit. What are some things we can do to improve that? Well, one thing we can do sometimes is we can cascade to op amps. That can lead to propagation delays, but usually the solution is to just get a better op amp, get an op amp with a better gain bandwidth product. So here's a term that's used more, not so much for op amps. This is a parameter that's used typically for power amplifiers, for audio amplifiers, and that's total harmonic distortion. Total harmonic distortion is one way of measuring sort of the purity or the quality of an amplifier by basically looking at if your amplifier is intended to amplify a single frequency, and so it has a single frequency at its input. The total harmonic distortion is a way of looking at the output and saying, what's the ratio of all the signal that is off frequency versus the ratio of the signal that's on frequency? So basically, this is a way of saying, as a signal propagates through an amplifier, it's going to get a bunch of distortion, not a bunch necessarily, it's going to get some distortion. And what causes that? We've talked about that before. That's mostly any distortion in a sinusoid produces, and you can think about it in the case of series expansion of a distorted sinusoid, it creates magnitude at harmonics of that primary fundamental frequency. And so one source of distortion in an audio amplifier is that, one source of measurable distortion is how much signal you get that's not the signal you're trying to amplify. And so you can measure that by basically taking the square root of the sum of the squares of the magnitudes of all these voltages, these off harmonic voltages, all of these off harmonic magnitudes. And so take the sum of the square root, take the square root of the sum of the squares of those voltages, divide it by your fundamental voltage, and that's a way to get total harmonic distortion. This method of measuring total harmonic distortion is typically used for cases where we're assuming the distortion is always just tweaking sort of warping the sinusoid. That's not the only source, though, of noise in an amplifier. In particular, with a Class D amplifier, which we talked about. Remember, the Class D amplifier uses this carrier frequency. It kind of has this high frequency carrier that produces a pulse wave. And that pulse wave has to then later be filtered out using an LC filter at the output. But there's still going to be some non-zero magnitude at that carrier frequency, at that pulse wave frequency. And that's not necessarily going to be a harmonic of the sinusoid. So that's a separate thing. So that's going to be this noise element too. So so total harmonic distortion plus noise, which is probably the more common one that you'll see. This is a way of sort of saying all the junk. It's all the junk at the output of the amplifier that's not what you want it to be, divided by what you want it to be, is the total harmonic distortion plus noise. So, and a lot of times with these, for analyzing these, it's fairly straightforward. And there's a problem in the homework that sort of asks you this, and I don't fully tell you how to do it, but I can kind of give you a hint here. If your circuit, if your output filter was an LC filter like this, for a Class D amplifier, your primary source of distortion is going to be that carrier frequency. So if you assume an input here, Vin of, a carrier, so that would be like, I don't know, if it's a 500 kilohertz carrier, it would be a 500 kilohertz wave at the full range of the voltage, right? So, if it's a 0 to 5 volt Class D amplifier power, it's going to be a 0 to 5 volt wave at the carrier frequency. And you can just treat that like a normal circuit problem. You can just say, okay, at that frequency, calculate the impedance for the inductor, calculate the impedance for the capacitor, treat it as a voltage divider, find the output voltage, find the magnitude of that. And then you can do the same for your signal. Your signal is going to probably be a much lower frequency. And because it's a much lower frequency, this capacitor at low frequencies is a bigger impedance, and this inductor at low frequencies is a smaller impedance. So for lower frequencies, you get much more of the signal across this voltage divider. I know it's not really a voltage divider, but I mean, it's basically that same thing, right? So if you think of a capacitor as something that's highly resistive to high frequencies, if you think of a capacitor as something that's highly resistive to low frequencies, and an inductor is something that's highly resistive to high frequencies, you can sort of see this thing as a sort of frequency dependent voltage divider. And that's effectively what's happening. Low frequencies show up as the input shows up almost entirely at the output, and high frequencies, the input is heavily attenuated at the output. And so you can, by actually calculating the magnitude of that and using these equations, well, specifically just, if you're doing a Class D, sometimes you just don't worry about the harmonic distortion. Sometimes just the noise, just the amplitude of that carrier. Find the ratio of those two, and that'll give you your total harmonic distortion. Now, this is normally done in a log scale too. So this is normally done as a log scale relative to the fundamental. So typically total harmonic distortion is going to be sort of a decibel scale kind of thing. Here's another one. The book doesn't really talk about this, but it's something that comes up a lot. So I want to mention it. I want you to know about it. This is spurious free dynamic range. This is kind of another way of measuring the quality of an amplifier, or it's usually more likely used to measure the quality of a generated signal or the quality of a sampled signal. But spurious free dynamic range is the amplitude difference between the signal that you care about and the largest off signal spur. So the largest, and again, if you think about a distorted sinusoid and you think about the series expansion of a distorted sinusoid, and you have this amplitude term in front of each of these harmonics, this is basically the amplitude distance between your signal and the largest harmonic. So it's not necessarily looking at the total magnitude of all those other harmonics. It's looking at what's the most pronounced harmonic and what is the distance in decibels between the signal you care about and that harmonic, which is also called a spur. A spur referring to kind of the peak that is off the main peak, right? So sort of just a peak, another way to say peak. So this is more often used in kind of radio applications. You hear this a lot in radios. You hear this a lot in when you are trying to reconstruct an audio signal. So if you have like digital data and you're trying to use that to reconstruct a sinusoid audio signal, spurious free dynamic range often refers to how good you're able to produce a sine wave from a digital representation of a signal. But anyway, I'm not going to talk much about that. You're not going to get problems on that. I just wanted you to know it exists. All right, on to the fun stuff, DC-DC converters. So DC-DC converters are everywhere now. And the reason they're everywhere is because transistor-based electronics are all powered by DC, almost all. There's some rare examples of transistor-based electronics that are AC, but nearly all of these things that we've come to rely on in our lives, I mean, even our light bulbs now are integrated circuits. Even our light bulbs are DC now. And so more and more stuff is DC powered, but transmission and distribution is almost all AC. Why is transmission and distribution almost all AC? Because it's really easy to transform AC. It's very difficult to transform DC, as you'll see. AC is easy to transform. What does it take to transform AC? 2 coils of wire and a bucket of oil. Right? If you go out in your neighborhood, you know, you see these little power poles, and up top, you see these little cans. What's that can? That can is, inside that can, we're going to X-ray vision here. It's basically 1 coil of wire and another coil of wire, and this is cartoonishly drawn, and it's inside a bucket of oil. Why is it inside a bucket of oil? Because if the insulation on these coils of wire starts to break down, you don't want it to produce ozone. And also, these can get hot, so you kind of want the oil to kind of keep things sort of cool. But that's all they are. You see those cans on top of your power poles. They're just 2 coils of wire and a bucket of oil. And that's all it takes to transform AC. That's why people love AC for distribution and transmission of power. It's easy to transform. DC, not so much. But then we have this initial problem of all of our power in our house. The little plugs on the wall, those little 2-prong things, they're AC. And the first thing we need to do to power all the fun stuff is to switch it to DC. So how do we do it? Well, this is the basic way to do it. You may have already seen this. I don't necessarily know all the curriculum we've had in the past. So you may have seen this. Normally, the way you do AC to DC conversion is you first step it down. So you'll typically go from like 120 to something lower, right? 17 or 9 or something like that. And this is done with a transformer. So this is typically done with just any sort of wall converter that's heavy has one of these in it, has a transformer in it. You don't have to do a transformer. There's, especially now, you get these like the little Apple devices, you get these little tiny wall plugs that sometimes they don't transform it. Sometimes they just keep it the full dose of the stars. They just keep it the full 120 volts, 170 volts peak kind of affair. So, but usually it's stepped down through a transformer. And then after it does it, it goes through a rectifier. This is a full wave rectifier, also called a bridge rectifier. You don't have to do this. If you wanted to, you could just do a single diode. A single diode rectifier is going to have a signal like this become a signal like this. So it's half wave rectified. Is that DC? That is DC. Current only flows one direction. So a single diode is all you need to make AC to DC conversion. But normally we prefer the full bridge. Why do we prefer the full bridge? Because then you get, boom. You take that negative hump and you flip it up, make it a positive hump. And the nice thing about that is you don't have this big gap here. So normally if you have a half-wave rectified signal, what's going on here? You're getting no energy from the wall at this moment. So in between these half cycles here, you're getting no energy. And what does that mean? That means you're going to have to pay for some sort of energy storage device, be it an inductor or a capacitor. You're going to have to pay for some energy storage device to store energy to keep providing it to your circuit in these little dead zones. Much better to do a full wave rectifier where you just have these little tiny little dips. Much cheaper capacitor, much cheaper inductor, whatever you need to store energy, much cheaper. And then they're just using a capacitor here. So what's happening is I didn't create this graphic. I don't know where I got it from. If I stole it from you, sorry. I don't know where it came from. I've been using it for a while. So I like it. So this is maybe not the best drawing of it. Maybe a better drawing of what's going on here would be something like this. Sorry. Because basically what's happening is shoot. Now it's getting bad now. So what's happening is basically when we're in these little lulls, when we're in these little dips, the energy stored in the capacitor is transferred to the output and the capacitor starts to discharge. And then as soon as the input voltage, as soon as this input peak is higher than the capacitor voltage, then the capacitor voltage is just going to follow that top of the peak. So this is shown as kind of a nice sharp sawtooth, but it's really more of sort of like the peak of a sinusoid followed by a decaying exponential. Peak of a sinusoid, decaying exponential, right? It's something a little more like that. I'm not an artist. I'll never be an artist. I could be a musical artist, though. You know that. You've heard Macy. I have that to fall back on. I got this face. I got these pipes in case this whole professor thing doesn't work out for me. Somebody who really likes turtles gets offended by what I say about turtles on here or something. Okay. So this is typically called what's called unregulated power. If you look at like what wall outlets, like everybody's got like a bucket at home of like their old like power converters. You never know when you're going to need like a wall outlet to barrel plug, and you just hope it fits in the piece of electronics you're trying to power. Typically everybody's got like a drawer of these plugs. And if you look at them, if you look at the back of them, they'll usually say like 120 volts AC to 9 volts unregulated. 9 volts unregulated means it's kind of 9 volts, but it's kind of got this messy ripple, right? It's about 9 volts. It's DC, so current only flows in one direction, and it's not, and it's somewhat filtered out, but it's not being controlled. We're not actively maintaining an exact voltage on that output. And then usually what we do is we take that, if we have like a 9 volt unregulated, we would then run it through some sort of voltage regulator, which produces a nice smooth output. So this is called a regulated output. And this is, we have a circuit that is actively controlling that output voltage to make sure it stays exactly at the desired voltage value. And this is the typical process for almost every single piece of electronics that you plug into a wall goes through. It usually goes through some kind of AC to AC step down, and then it gets rectified to an unregulated DC voltage, and then it gets regulated down to a regulated DC voltage. Why does a regulated DC voltage matter? Because the types of electronics that we use behave differently at different input voltages, and they also can break at certain input voltages. So if the input voltage is too high, it's possible you're going to damage those electronics. And if the input voltage is wiggling around a lot, it's possible you're going to get unknown, undefined behavior of those electronics. So what type of regulators do we have? Let's start with the Zener regulator. This is the most basic type of regulator you have. Imagine you just simply took a Zener diode and you oriented it like this, and you had some resistance just so you don't have, unlimited current flowing through the Zener diode. And what does a Zener diode do? A Zener diode will break down, right? It has sort of, it operates in this reverse breakdown region. So at a very certain voltage, at a specific voltage, remember the Zener diode, right? Zener diodes have this reverse breakdown. And so operating it in reverse, there's going to be a very constant voltage across this, right? It doesn't matter how much current really is flowing through it, this voltage value is going to stay the same. So if we think about this circuit, how does this operate? If we think about this, oh man, not my day. If you think about this circuit, then you're going to have some constant voltage across it, right? So there's going to be the Zener breakdown voltage across the Zener diode. So that's the voltage your output's going to see. And this works, but it's not great. Why is it not great? Because if this load resistance gets too small, so if the load starts drawing too much current, it's possible for this voltage to drop below the Zener voltage. If this resistance gets too low, then this resistor and this resistor are basically going to form a voltage divider. And at a certain point, that voltage is going to drop below the Zener voltage. So you might say, okay, we can fix that by just making this R very small. Well, that's okay. But then if this load is big, you are burning an enormous amount of current through this Zener diode if you're going to play that game. So Zener regulators work. They usually, people actually still use them. So people still use this sort of thing, but they generally use it only when they have a very small current requirement. They have a very strict cost requirement. So if they really can't spend a lot of money to build this regulator, and it's a small current and it's well-defined current, then sometimes this works, but this is uncommon. It's uncommon to use this to power electronics. Let's just say that. So something a little better is what we call a linear regulator. So a linear regulator is similar, right? We still kind of produce we still use a Zener diode and a resistor to produce a reference voltage. But now in this case, what we're doing is we're using that to, instead of powering a circuit, it's driving a transistor, which is driving the circuit. So we can get a gain amplification. So now basically we can have 1/50th the current flowing through the Zener diode that we have flowing to our output. So we're using this voltage reference. And if you think about this, the way this works is this voltage V out is going to be VZ plus 0.7. Right? If we have or sorry, going to be, yeah, VZ, sorry, VZ minus 0.7. So we're going to have this voltage drop between the across the BJT, across the and so it's a little off from the Zener reference, but whatever, we can choose it appropriately. The main thing is we're going to use that amplification of the transistor to improve the efficiency this way. So if this voltage ever drops below this, if this voltage drops below VZ minus 0.7, now we're going to start to get this voltage across here that's greater than the threshold voltage, greater than that 0.7. We're going to get a large amount of current that flows through the base, which then creates, that amount of current times 50 or 80 or 100, or depending on the transistor you're using, flowing to the output. So small change gets a big amplification, which corrects that voltage then. So we never have a very big deviation. If we had a big deviation, it would result in a large change in current flow, which would correct that deviation. And there's another way we can do this. We can also do this. Sometimes it's inconvenient to do a design like this where we have to choose a Zener voltage. We have to choose a Zener diode that's tuned to the exact voltage we want. It's much better to basically just use a resistor divider. We can use a resistor divider to take our output voltage, divide it down to a set voltage, which is chosen by this Zener. So in this case, VP. So in this case, VP equals VZ plus 0.7. So let's say VZ in this case was 1.8 volts. Then VP would be about 2.5 volts. So in this case, this circuit would regulate the output voltage to whatever voltage it needed to be to maintain VP at 2.5 volts. So in this case, all we have to do to change the regulated output voltage is change that ratio of resistors R3 and R4, and that's a programmable linear regulator. So this is probably more common. You'll see this more often. This programmable linear regulator is sort of the more standard type. A little more versatile. And okay, let's talk a little bit more. So we showed it just now with BJTs. You can, it's more commonly modeled as an op amp. An op amp is going to get better performance there. So, and an op amp again is pretty much just a collection of BJTs that are just cascaded to get higher gain. And the higher gain you get, the smaller error you're going to get in your output with a linear regulator. And there's a couple things to talk about with this, though. So yeah, it can be internally programmed, or it can be externally programmed. The nice thing about internally programmed ones is these are 3-terminal devices. So all you need for a linear regulator that's internally programmed is an input voltage, a ground reference, and an output voltage. That's it. You can also have an enable if you want. And of course, programmable resistors or programmable linear regulators. This is an ADP123, very standard footprint, very standard type of design. Again, choose a ratio of resistors so that at your desired output voltage, you're getting the appropriate voltage at this feedback pin, and it'll regulate to that. It'll regulate to keep that voltage of the feedback pin constant. The corresponding output voltage will be based on that resistor divider. There are special types of linear regulators called LDO, called low dropout linear regulators. Typically, these are linear regulators where they're able to have a voltage difference between the input and the output of less than 0.7 volts. So if we go back, looking at this circuit here, would it ever be possible, like let's say V in was 12 volts, would it ever be possible for V out to be 11.5 volts? No, because for V out to be 11.5, then this voltage here would have to be 12.2, and there's no way, right? So you'd have to have current flowing backwards through here. So that's not going to happen. So basically, because of this threshold voltage drop across the BJT, there's no way for this linear regulator as shown here to have an output voltage that is within 0.7 volts of the input voltage. But a lot of times we don't want that, right? Like let's say we have a circuit powered by a lithium polymer battery. That lithium polymer battery might drop down to 3.7 volts, but let's say we want a circuit that's regulated to 3.3 volts, which is a very standard voltage for digital electronics. Well, a 3.7 volt input voltage regulated to 3.3 volts, that's going to need a 0.4 volt drop at a maximum. So that means that this is right out the window. And there are low dropout regulators basically replace this. And we can kind of go here. They basically replace this transistor with a Pmos transistor. So what's the good thing about a Pmos transistor? A Pmos passes a clean one, right? A Pmos passes a clean high voltage. So they put a Pmos MOSFET at that high side, which allows them to have a much smaller voltage drop between the input and the output for regulation purposes. So that's how a low dropout regulator works. What's the downside of using a Pmos on the high side? Pmos typically have poor or they have worse conduction properties than they have a more resistive channel due to the mobility of holes versus electrons than an NMOS transistor. So something to keep in mind. LDO regulators tend to cost a little bit more. They cost more to get the same sort of maximum current output because PMOS transistors just aren't as good. Maybe they have slightly worse frequency performance too, but it can be really nice to be able to have an input that's very close to your output voltage. Output current is an important limitation of these. Output current a lot of times has to do with thermal handling. So one thing about these regulators is they are burning power across that transistor. The way they get a voltage drop between the input and the output is by restricting the flow of charges through that transistor, which produces a voltage drop across the terminals. Whenever you have a voltage drop and a current, you got power. So it's burning power to produce that voltage drop, and it's got to go somewhere. That energy has got to become heat. It's got to get dissipated. So that can be a problem. It can make LDO regulators. It can make linear regulators a bad choice. You're going 12 volts to 3 volts. You got 1 amp. That's a lot. You're burning 9 volts at 1 amp. You're burning 9 watts if you choose a linear regulator. So there's other better choices for that. Sometimes you just don't care. Sometimes you just burn it. But normally you'd probably care about something like that. There's a limit to your input voltage range and to your output voltage range. So you always got to check the data sheets for your designs for these. And as I mentioned, total power dissipation typically having to do with thermal limits of the device there. So moving on from LDO regulators, from the issue we just talked about with LDO linear regulators or just linear regulators is sometimes people just call them LDOs, right? Just referring to low dropout, just as another way to refer to the standard linear regulator. The downside is they adjust voltage they just burn voltage. So the input current is the output current, and they just burn voltage across a transistor. That's how they drop the voltage. Switching supplies give an option to be a little more efficient. And the idea behind a switching supply is kind of what we talked about with the Class D amplifier. The idea behind a switching supply is if you have an input voltage and you want to produce a smaller output voltage, one thing you can do is chop the input voltage up such that the average voltage you produce is your desired voltage, and then smooth it out. So take your input, chop it, average it, and smooth it. And that's a good way to go from here to here, right? So, okay, so the nice thing about switching supplies is they are efficient, but they are noisy, right? This chopping produces a lot of noise, and that noise you generally have to clean up, and it's usually kind of expensive to clean that up. Inductors are not cheap. Capacitors are not cheap. You have to pay for these to clean this switched signal up. And also that noise is more than just the signal. The noise matters more than just having a signal that has to be LC filtered or just capacitively filtered. Noise also produces noise that interferes with other things in your circuit. So switching supplies are notorious for interfering with analog signals. If you have a very sensitive analog signal, you probably want to keep that signal very far away from your switching supplies, because these switching supplies have a lot of current typically flowing through an inductor. And when an inductor is a big coil of wire, it's going to radiate electromagnetic flux. It's going to produce stuff that's going to interfere with traces on your board. It's going to interfere with other nearby wires. So long story short, noise is more than just signal noise. It's also environmental noise. It interferes with other signals in your design. So simplest type of switching regulator is a buck regulator. It's kind of what we just talked about. You have a switch. You're setting a duty cycle of the switch in order to drop the average voltage from the input to the output. And then you are filtering it through an LC filter. And again, just like the Class D amplifier basically did this. Class D amplifier kind of is a buck regulator that's just dynamically changing, right? It's like a buck regulator that's changing the voltage it's driving to constantly to generate that audio signal. And okay. Now, one thing we do is when we show these simple little graphical designs, we just say, oh yeah, there's a switch, and the switch is doing this, and it's making a pulse train, and that's all. It's just switching a pulse train. But there always has to be a controller for that. So all switching regulators, ultimately, they have some sort of a controller that is actively changing this duty cycle. It's actively changing this pulse width in order to maintain that constant output voltage. If the output voltage starts to get too low, it's got to increase that duty cycle to increase the average coming out to boost that voltage up. And so that controller, that logic controller, and the switch and the gate driver for this MOSFET, for this switch, all that adds cost and complexity. So it's what, you know, it's these things look simple when they're just a switch and an inductor and a capacitor, but they are not necessarily. Did I not show the diode? I did show the diode here. What's this diode here? Why do we have that there? Switch, produce a train, a pulse train, and then it gets LC filtered. What's the reason for the diode? The reason for the diode is when this switch opens, right? So when this switch is closed, we have current flowing through the inductor. And then what happens when this switch opens? Well, if this switch opened and this diode weren't here, we would be open circuiting an inductor. What does that do? Well, unfortunately, an inductor, the current through an inductor cannot change instantaneously. So if you open circuit an inductor, you're going to get a massive voltage spike on the other side of it. So you would get a huge voltage spike here. And what the diode does is the diode allows current to keep flowing through the inductor. So you allow current to keep flowing. When this circuit is open, you allow current to keep flowing through this little mini circuit over here using this diode. So sometimes there's a lot of different names for it. Some people will call that a freewheel diode. Some people will call it a flywheel diode. Some people call it there's lots of names for it. But basically, it's the diode that allows current to keep flowing. It's the diode that prevents you from creating this massive, negative 3,000 volt voltage on the other side of that inductor the moment you open the switch. So. So it's a fairly simple design. The idea behind a buck regulator is fairly straightforward. Chop up an input voltage so the average is less, smooth it out, have a controller which changes the duty cycle if the voltage gets too low or too high. But how do we actually design these sorts of things? How would we actually, it's one thing to just say symbolically, this is how it works. What about what about choosing values? What size inductor do I need? What size capacitor do I need? What's my frequency of operation? Well, I've found the best way. The book goes through this. The book has a chapter kind of talking about this, but this is one area where I like to go straight to the source. I like to, right? If you want to learn about smoking, you can learn about it from government health experts or straight from the Lowell Large Tobacco Corporation. this Manitoba's, right? Yeah. It's not showing him because I got my virtual background going. Anyway, he's someone. Yes, I still have him here. I don't clean my shed out very often, so if I do something, it's all still around me here typically. So Texas Instruments makes a lot of switching regulators, and so they produce a lot of these application reports that say, hey, if you want to know how to design a regulator, here's the process. Here's what our engineers do. It's good enough for TI, it's probably good enough for us. Now, here's the reality of it. The reality of it is if you're doing a proper analysis of a switching regulator, it's actually very complicated. And the reason for that is the switching regulator goes through several phases. It goes through the switch being open. It goes through the switch being closed. But it also goes through this little transient, which is as the switch is opening and as the switch is closing. That's a critical little piece in there. And the issue is with a normal analysis of a switching regulator, you kind of have to do a piecewise analysis of all four parts of the design, of the open, switch closed, switch opening, switch closing. There is a class that we teach. We do teach an energy course here that goes over that does that kind of analysis. For the purposes of this class, we're going to be a little more meat and potatoes. For this class, we're going to sort of say, let's just say you're building a regulator. How would you actually build the stupid thing to put on a board to do a design for a product? And that's where these sorts of application reports, these sorts of white papers are really useful. And the nice thing is Texas Instruments updates these as needed. If their engineers start doing something different with the way they design their buck or boost regulators, they update their application report. And that's what happened here. This application report written in 2011, revised August 2015. So somebody probably said, yeah, there's something I don't like about this. Let's update it. So it's kind of like a free textbook. It's like a free mini textbook. So thank you, Bridget Hawk. Is that? I don't know who Bridget Hawk is, but thank you. I appreciate it. It's a very nice document. It's posted on our course page. So if you look inside one of the file folders, there's this, you can search for it. You can search for just SLVA 477B, and you'll find it. If you Google search it, I'm sure it'll be the first thing you find. But what I've done is I've taken that document, and for the purposes of this presentation, I've chopped it up. I've taken the important bits out of it. I've condensed them into a couple of slides, so we're going to talk about that. So for the kind of basic op-amp or basic buck regulator design here, one thing is, what's that duty cycle? Well, the duty cycle is the ratio V out over V in. That should be fairly obvious, right? The duty cycle tells you what fraction of the output is, what fraction of the input is the output. So it's fairly obvious that the duty cycle is going to be V out divided by V in, but it's also sort of times this efficiency fudge factor. So there's this little efficiency fudge factor where, although ideally this is sort of a lossless design, there's no losses here. There's of course going to be some loss with the diode, I suppose. There's going to be loss in the resistance of the switches and the inductors and the capacitors and things like that. But they're lumping it all into this term here. So they're saying there's this efficiency term. And normally this is going to be, for most buck regulators, this is going to be about 0.75 to about 0.9. So 75 to 90% efficiency is fairly common for most buck regulators. And it's not unreasonable to operate here. It's really not unreasonable to operate close to 90% efficiency for these buck regulators. And the problem is it's a little bit of a chicken and the egg. You kind of have to, you know, your efficiency is going to be based on your design setup, but you need to know the efficiency to do the design setup. So one thing that they tend to do is they'll show application curves. So they'll have curves that show you, that help you ballpark what your efficiency is going to be before you even start doing your regulator design. And I show one of those in a later slide. I don't know why I don't have it on this slide, but I don't. So the inductor ripple current, the ripple current is, that's what's happening is, if you look at this inductor, when the switch is closed, this inductor current starts to increase. And then when the switch opens, that inductor current starts to decrease as it drives the circuit. Switch closes, switch opens, switch closes, switch opens. And that's this ripple. So that's this inductor ripple, or what do they call it here? Delta I. Delta I. Oh, it's terrible. It's terrible, right? So, but that's the ripple. You get the idea. It's the current ripple. And, you know, usually, so that current ripple is a function of this Vin max minus V out times duty cycle divided by the switching frequency. The switching frequency is usually set by the manufacturer, so you don't usually get to control that, times this inductance. And this is all well and good. The problem is we need to solve for this, you know, we need to solve for this. We're not, and so we kind of need to guess this. So usually with inductor ripple, there's kind of a rule of thumb where you typically want the ripple to be anywhere between 20 and 40% of your output current. And that's kind of what they say here. So usually you'll just kind of say, yeah, let's keep the ripple to maybe 30%. If you're okay with your circuit being a little more noisy, you know, maybe you push it to 40%. If you want it a little bit smoother, maybe you do it closer to 20%. This ripple also matters a lot in terms of the noise you're kicking out to the rest of your circuit. If you're allowing this inductor to sort of fully charge and fully discharge with each cycle, then you're going to be producing a lot of electromagnetic flux. You're producing a lot of noise for other stuff in your circuit. So sometimes you keep the ripple down, not only for minimizing the output ripple, but so that if it's next to something that's highly affected by this noise, it kind of reduces that a little bit too. Okay, so working backwards, if we're trying to pick a value for our inductor to go here, we can do that with this handy equation. The inductor is going to be our V out times V in minus V out divided by this current ripple, which again, we're going to rule of thumb that. We're going to have to just pick something for our current ripple, give it a good rule of thumb, and times the switching frequency times the input voltage. So this is a nice little equation we can use to calculate what size inductor do we need here. So for the project that we did, most of you used a 4.7 microhenry inductor. We did that because we kind of pulled it from the data sheet, but if you wanted to actually calculate, if you wanted to go back and calculate the expected parameters for that switching regulator, it's not a buck regulator, it's a boost. We'll talk about that in the next video, but you could do that here. So, okay, a couple other parameters here. I'm going to kind of skip some of these. Some of these don't matter as much. The big thing is this is how we solve for the inductor value we're going to need. Now, what about the capacitor value? Well, the inductor value is needed in terms of solving for your ripple, in terms of minimizing your current ripple. But the output capacitor minimizes your voltage ripple. So your inductor controls current ripple, output capacitor controls voltage ripple, but they're related to each other. So obviously, the bigger your current ripple, the bigger your capacitor you're going to need to get a nice clean output ripple. So, and the equation is fairly straightforward. The capacitor you need at the output is going to be your current ripple divided by 8 times your switching frequency times your delta V out. This is your voltage ripple. Voltage ripple. And what decides what your voltage ripple is? It's usually a parameter of the electronics you're using. If you're using a microcontroller, it'll usually say you have to power this microcontroller with between 2.7 and 5.1 volts, and it must have an input supply voltage ripple of less than 50 millivolts or something like that. They'll tell you usually. And then you generally want to have a safety factor. You usually don't want to just push it to the limit. So you usually want a little bit of a safety factor. Also, it should be noted that if your capacitors have an equivalent series resistance, which they all will, that's going to impact it. So the series resistance is going to add to output voltage ripple as well. And what that means is using a better capacitor, it's not just about is the capacitor 10 microfarads or 5 microfarads or 2 microfarads. It's also about if you have a good 10 microfarad capacitor that has a very low equivalent series resistance at the frequency of your switching, well, you're going to get less output voltage ripple. This is what I was talking about in these sort of efficiency curves. So if you look at the data sheet from almost any regulator, it'll say, all right, if you're trying to output, this is for a boost regulator, but you get the idea basically. It's saying basically for a certain output voltage, for these different input voltages, your efficiency is going to be given by these graphs based on your output current. So for your application, generally when you first start, you can look in the data sheet, you can say, I'm going to be outputting 100 milliamps and my input voltage is this, and my output voltage is this. So based on this curve, yeah, I'm going to be about 80% or something, right? So you can usually kind of get your efficiency right off the bat or get your approximate efficiency early on. And that's usually something that tells you whether or not this is the switching regulator for you. If you're operating kind of out in the weeds over here with your regulator, you might want to upgrade yourself to a slightly bigger, better regulator. You don't want to push it. You notice these curves fall off pretty fast. That's fairly standard for all switching regulators. So you don't want to operate in here. You want to be operating, somewhere in this territory here. Okay. Now the other thing is, when we're talking about output capacitance here, this is assuming that we have a sort of a constant current draw. This is just kind of assuming constant current ripple just produced by the switching event in the switching regulator. But there's another type of output, not ripple. There's another type of output deviation, and that's caused by rapid changes in your current draw. So if you have a circuit that's consuming 20 milliamps, and then all of a sudden it starts consuming 20 microamps, the switching regulator is not going to immediately compensate for that. And typically it's that if you do a switch like that, you're going to have an overshoot. You're going to have your voltage go higher than what it's supposed to be. Or if your current output is 20 microamps and then all of a sudden it switches to 20 milliamps, you could have current undershoot. So sometimes you want to design your output capacitor to minimize these sort of overshoot, undershoot events, and that's where you're going to use this equation here. Does that actually happen? You might say, come on, 20 microamps to 20 milliamps. When does that happen? All the time. All the time. When? Pause the video. Think to yourself, when is my circuit going to go from microamps to milliamps or milliamps to microamps? Pause it. Answer it. Be honest. Think about it. Welcome back. We had some thoughtful self-reflection. What did we come up with? Power saving modes. When things go to sleep, when things go to low power modes, microcontrollers don't want to always be consuming milliamps of current. Your microcontroller probably is going to wake up, do something, go back to sleep. And when it goes from doing something to going back from sleep, 20 milliamps to 20 microamps. It could be 20 milliamps to 20 nanoamps, right? I mean, like some of them really sleep nowadays. So power save modes is low power modes, power save modes, sleep modes. These are typically where you'll see these rapid changes in current. And this is where you can kind of have these sort of overshoot issues. A lot of people have this problem where they'll have a device, they'll do a design, and they'll say, every time this thing goes to sleep, it restarts. And sometimes they'll say, what on, like every time it goes to sleep or when it wakes up, it restarts. What is going on? Those sleep and wake up events are pretty critical events. So if something goes wrong, there's a lot of things that can cause something to go wrong at a sleep or wake up event. But sometimes it's really good to put a scope on your power supply and check those. So look at what the supply does when it goes to sleep and when it wakes up, because you could be getting an over voltage or under voltage event. And how would you fix that? More capacitance, fork out a little dough, get yourself a better capacitor, bigger capacitor, lower ESR. There's no way. You got to pay up. You don't want it to break down. Okay, let's do an example. Oh, shoot. I don't think I finished this slide. All right. We're working without a wire then. So we have an example here. You have a 12-volt input supply that you need to buck down to 3.3 volts. Output with 2 amps peak output current. Your buck regulator operates at 84% efficiency. That might not matter for us, but and you need to keep your current ripple to 30% of peak and your output voltage ripple to less than 100 millivolts. Choose an appropriately sized inductor and capacitor for this application. All right, first thing we're going to do is we are going to go to the inductor. So going back to this equation here, inductor is going to be V out times V in minus V out. That's going to be, so V out was 3.3 volts times V in minus V out. That's 12 minus 3.3. Trying to swipe back. Divided by delta IL times frequency times Vn. Oh, I don't even say. And our Vn was 12. I don't say. All right, so this is a, let's go with the standard. Let's go with 1.1 megahertz. Megahertz. So we're gonna have a switching frequency of 1.1 megahertz. Modern buck regulators commonly operate at 1 megahertz or more. So high-powered ones tend to operate a little slower. The high current ones tend to operate closer to the hundreds of kilohertz range. Why is that? It's because the high current ones are driving a very big transistor to allow that much current to flow. And the problem with driving very big transistors is they have very capacitive gates. And the problem with very capacitive gates is you can't charge and discharge that capacitor instantaneously fast. So if you're switching too quickly, you're gonna spend almost all your time in these sort of transition events where you're opening or closing your transistor. And those are the bad ones. Those are inefficient. You don't want to be doing that a lot. So they'll generally slow it down to drive the gates of a bigger transistor for high power applications, and it means you need bigger inductors and capacitors. But for normal current applications, 1.1 megahertz is very reasonable. So our frequency switching here, it's going to be 1.1 times 10 to the 6th. And then delta IL, we said our ripple current, 30% of peak. Now, here's my question is my ripple, yeah, 0.2 to 0.4 of our output. So and then we said 30%, so 0.3 times output was 2 amps. So this is going to be, okay. So I totally flubbed this slide. I'm not going to redo it. I totally flubbed this slide though. 3.3 times, you got to check my work here too, because I screw these up all the time. So I'm getting 3.625 microhenries. Okay. So we're going to need at least a 3.625 microhenry inductor to keep our ripple low. Now, normally you wouldn't just do 3.625. You don't get to choose inductors to every single possible range. Normally you'd choose like a 4.7 microhenry, something close to that, sort of the next step up in ones that you can find that aren't ridiculously expensive. So, but for now, we did our solution. We need a 3.65 microhenry inductor. What about the next thing? Keep our voltage ripple to less than 100. Well, let's go back. What's our voltage ripple? So our C out is going to be delta IL, which we know was 0.6 amps, divided by 8 times frequency switching times delta V out. So we're going to have, oops, let's give ourselves a little space here. What am I doing? So we had 0.6, my memory's bad. 0.6 divided by 8 times, divided by 8 times switching frequency times delta V out. So our switching frequency was 1.1 times 10 to the 6th. Our delta V out was 100 millivolts. Let's do that. I'm getting so I'm getting 68 10. Is that right? Nope. Nope. Yeah. So I'm getting 681.8 nanofarads. So about 0.7 microfarads here. Okay. And again, in this case, you'd probably air up. You'd probably air up to a 1 microfarad output capacitor at least. And you might even go bigger than that. And I mean, 100 millivolts ripple isn't great. It's kind of a lot. So we're kind of being, this is a rough cut here. But you're getting close to 4 microhenries for your inductor, close to 1 microfarad for your capacitor. These are kind of ballpark ranges for these types of devices typically. So that's how we do it. That's all. It's really handy to be able to know this process. What are the things you need to know about your? Oh wait, first of all, where did the efficiency come into play here? It didn't. Right? So let's ask a quick question that relates to efficiency. What's our input current? We can ask that right now. What's the input current for this? There's a couple ways to find it. The easiest way, though, is to just do it based on power and efficiency. So our output power is going to be 3.3 times 2. And this is peak. Everything here we're doing here is peak. 3.3 times 2, that's going to be 6.6 watts. And this is 84% efficient. So if we got our input power, that's going to be 6.6 watts divided by 0.84. That's going to be 7.857 watts. So now we can find that input current. So our input current is, our input current is going to be the power divided by the voltage. So that's going to be 7.857 divided by 12. Now this is neat. So with this sort of a regulator, we had 2 amps output current and only 655 milliamps input current. This really shows the advantage over a linear regulator. If we had used a linear regulator for this application, 2 amps out would have been 2 amps in. So rather than consuming 2 amps of current at 12 volts, Using a buck regulator, we're consuming 655 milliamps of input current. This is a real advantage to this. It's also an interesting thing because if you look at like cell phone chargers for your car, there's two types. You know, cell phone chargers that go in your cigarette outlet. Some of them are linear regulators and they get warm and they're very inefficient. And some of them are switching regulators. Nowadays, they're mostly switching regulators, but you'll still find some that are linear regulators and they dissipate a lot of heat. And because in a car, you're going from about 14.5 volts down to 5 volts for a cell phone charger. So if you're using a linear regulator instead of a switching one, that's a big efficiency difference. Okay, that is enough for now. So this is a long enough video. The next video, we're going to talk about boost regulators. And boost regulators are a little bit more complex, but it's kind of the same basic idea. Our analysis is going to be the same as well. So there's the Texas Instruments white paper on designing boost regulators that's available on the Canvas page that you can look at now if you want. So I will see you next time.